Section 7.8 is about improper integrals. And there are two cases where we have improper integrals. The first one is that we have infinite integrals. This is when we have a continuous function, but the integration goes like from 1 to infinity of f of x, or from negative infinity to a value, or both. It can go from negative infinity to positive infinity. And the second type comes from discontinuous functions. So consider the integration from negative 1 to 1 of 1 over x dx. We know that 1 over x is a discontinuous function because it has a vertical asymptote at the y-axis. So this is an improper integral. Whenever we have improper integrals, what we're going to do is we're going to look at the limit, and we're going to use limits and what we know about limits to evaluate those. What we do discover is that there are two types of answers. We say that the improper integral is convergent if the limit exists, and it's divergent if the limit does not exist. We say if the limit does not exist. Now, all the directions in all of the books tell you to determine convergent or divergent, and then if it is convergent, find the value. But here's the hint. Convergent, the limit exists, so you get an answer L, which is some number. And here, divergent, your answer will either be infinity or negative infinity because it does not come out to a value. So you actually have to evaluate them, and after you evaluate the integral, that's how you'll be able to determine if it's convergent or divergent. So let's look at an example. The first one is example 1, and it says the integration from 1 to infinity of 1 over x dx. So your thought is, first of all, there's an infinity here. You can't name infinity. Infinity is a very, very large number, and Buzz Lightyear says to infinity and beyond, but you can't go beyond it. You can't name it, so you can't integrate at it. And if we look at the definition of a improper integral, then the definition tells us that if the integral exists right here, then we take the integral and we look at the limit. Notice that we change the upper bound from infinity to t, and we take the limit as t approaches infinity. So that's how you handle this, provided the limit exists as a finite number. So you have to remember your definition of a limit. The left-hand limit has to equal the right-hand limit. The limit exists if the left-hand limit equals the right-hand limit, which means it's continuous, and the value is equal to the limit at that value. Most of ours work in that area. The rest of them fall under discontinuous, and we're going there. But notice that happens here as well. Our lower bound is negative infinity, so we do the limit as t approaches negative infinity. So if we have both the integral from negative infinity to positive infinity, we're going to split it and then use the two definitions up above. So what's important is that you can't integrate to infinity or from negative infinity because they are not solid concrete numbers. You have to use integrals to do such. So let's go back to this example. So the key step here is we say the limit, as they use t, I'm going to use the letter m. As m approaches infinity, the integral from 1 to m of 1 over x dx. That's the key. So then you go ahead and we're going to do the integral, but we need the limit each time. So we're going to bring it down and say the integration from 1 to m, but we know what that is. The integration of 1 over x is natural log of x from 1 to m. Now I started this, but I forgot, so let's go back. Y equals 1 over x looks like this in this quadrant. So from 1 to infinity, it just keeps going. So it is continuous, and we're okay to use this method. So now we say the limit as m approaches infinity. So we have the natural log of m minus the natural log of 1. Now the natural log of 1 is 0, so we say the limit as m approaches infinity of the natural log of m really means the natural log of infinity, which is infinity. Now, since we got infinity, we say divergent. If we'd gotten a number, say a half or a third or 3/4 or -2, we would say convergent. But when your answer goes to infinity or negative infinity, the answer is divergent because the limit does not exist as a finite number. And since the limit does not exist as a finite number, then the integral is divergent. Let me say that to you again. Since the limit does not exist as a finite number, the integral is divergent. Think about your definition of convergent and divergent. So if it goes to a finite number, then it converges to that finite number. Let's look at another example. It says the integration from negative infinity to 0, x e to the x dx. So we start off with, we need to use a limit, and I like m, your book likes t, so I'm going to put m down here in place of negative infinity and 0, x e to the x dx. Now x e to the x is integration by parts, so let's go ahead and set that up. We have u and v, du and dv. So u is x and dv is e to the x dx. So let's fill it in accordingly. And when u equals x, then du is just dx. And when dv is e to the x, then v is also e to the x. So now you got to carry your limit until you perform the limit. So bring it along. And we're going to say x e to the x from m to 0 minus the integration. So it's uv minus the integration of v, which is e to the x, du, which is dx, from m to 0. So we have the limit as m approaches negative infinity. I left that off. Let me throw that back in. As m approaches negative infinity, we still have x e to the x minus, I'm going to wait and put bounds on the end and let that parentheses carry. The integration of e to the x is e to the x from m to 0. So now we say the limit as m approaches negative infinity. Now let's plug in the value of 0. So we have 0 minus 1. That's when we plug in 0. And now let's plug in m. So we'll have m e to the m minus e to the m. Now this gets a little tricky here because you have to remember L'Hopital's rule. Hold that thought for a second. So we have negative infinity. So here I have negative 1. And then we have minus m e to the m plus e to the m. I don't know that it's any easier to factor. So let's look at it term by term. Let's look at it term by term. The limit as m approaches negative infinity of negative 1 is negative 1. Now let's take a note over here and let's look at the limit as m approaches negative infinity of, we have the term negative m e to the m. Now remember, e to the m is, this is e to the negative infinity. And if you think about e to the negative infinity, e to the infinity, e looks like this. So as we approach negative infinity, as we approach negative infinity on this graph, we're approaching a y value of 0. So this is technically 0, and this is negative infinity. So we have a negative infinity times 0. That's an indeterminate form. Do you see where these came from? Let me do that for you one more time, kind of in order. So what we have here is we have negative infinity, and then we have e to the negative infinity. So we technically have positive infinity times 0. That's an indeterminate form. Do you see where that 0 came from? Because e to the negative infinity, e to the x goes up, and as we look at it going out towards negative infinity, we get closer to the x-axis of 0. So what we need here is we need L'Hopital's rule, because we can't have 0 times infinity. And we show that by saying infinity times 0 is an indeterminate form. So L'Hopital's rule, you need a fraction, first of all. Let me remind you about L'Hopital's rule. L'Hopital's rule has 3 conditions. First of all, you need a limit. Secondly, you need a fraction. And thirdly, you take the derivative of the top separately from the derivative of the bottom, or the derivative of the numerator separately from the derivative of the denominator. So if we look at this problem, it says the limit as m approaches negative infinity, and we have negative m e to the m. So what we need is we need a fraction. We have a limit, we need a fraction. We have a limit with an indeterminate form. So with an indeterminate form, so we take the limit, let's say negative m over e to the minus m. We can move that e to the m to the denominator with a negative exponent because that's the same problem. So now we have a limit. Now we have a fraction. So we can, L'Hopital's rule says to take the derivative of the top and the bottom separately. This is actually the rule. So we're going to say the limit, and usually we say out here that we use L'Hopital's rule. So the limit as m approaches infinity. Now the derivative of the top is negative 1, and the derivative of e to the something is e to the same thing, and it's chain rule, so we have a negative 1 here. So this means that we have the limit as m approaches infinity of 2 negatives make a positive over e to the minus m. Now remember that that's e to the minus m. Left off my negative on my infinity again. So remember this is e to the minus m, so it can move up as e to the m. Now we go back to that example, and here's e to the x. So as we approach negative infinity, still we are approaching 0. So this answer is 0. Pause it, think about it, come back, hit it again if you need to. So what we can do is we can come here and say this middle term becomes 0. And the last term says, if we look at the last term, it says the limit as m approaches negative infinity of e to the m, and we've already determined that to be 0. So we can come back into our problem and say 0. Now, it is better to put this in the problem, but I kind of wanted to pull it out for you to see that this means our answer is going to be negative 1. But if you're writing this problem up, you either need notes in there or you do it each time. So we're going to say the limit as m approaches negative infinity of negative 1 plus the limit as m approaches negative infinity of negative m e to the m plus the limit, I'm going to run out of space, let's do it here, plus the limit as m approaches negative infinity of e to the m. Now, this one's not too bad, like we talked about. So we have negative 1 plus the limit as m approaches negative infinity. Now, what we need here is we need L'Hopital's rule. This is a nice review because we already did it, but let's pretend we have not. So we have negative m over e to the negative m. Because I have a limit, I have an indeterminate form. In my head, I can see that this is infinity times 0, which is an indeterminate form. So I'm writing it as a fraction, so I can use L'Hopital's rule. Some people pause here and just work all the way down. You can go either way. Plus, and I know this is 0. So we have negative 1 plus the limit as m approaches negative infinity. And the derivative of negative m is negative 1. And the derivative of e to the negative m is e to the negative m times negative 1. We don't need to write that plus 0 on the end. So we have negative 1 plus the limit as m approaches negative infinity of the two negatives make a positive, and we can move the e to the m up. And we already know this is 0. This is 0. Let's go back to this graph, because as I read my e to the x graph out to negative infinity, I approach 0 for the y value. So this answer is negative 1. Now, since we have a finite answer, I started to write divergent, got carried away there. Since we have a finite answer, this answer is convergent. We have a finite answer, therefore the integral is convergent. Let's consider another example. It says the integration from negative infinity to infinity of 1 over 1 plus x squared dx. Now you put this graph in your calculator and you find that it looks like this. So it is continuous. That's important to note. That means you can split this integral any way you want to, but you need to do two separate integrals because we have from negative infinity to positive infinity. So we're going to integrate, first of all, from negative infinity to 0, because 0 is our easiest place to split all the time when it's allowed. And then we're going to integrate from 0 to infinity. I tend to carry both of them at the same time, especially with them being similar like this. A lot of people do them separately, so let's take the first one, and let's say we're going to integrate from negative infinity to 0, 1 over 1 plus x squared dx. So we're going to say the limit as m approaches infinity, m to 0, 1 over 1 plus x squared dx. Now I know that this is inverse tangent. So we have a equals 1 in this case. Remember that the integration of 1 over x squared plus a squared dx is 1 over a inverse tangent x over a plus c. That is on your reference paper that I give you. So what we're going to do here is a equals 1. So we have 1 over 1 inverse tangent of x over 1, which is just x. And we are going from m to 0. And we're in that limit. I keep leaving my negative infinities off. I apologize for that. So here we have the inverse tangent. So we say the limit as m approaches negative infinity. We have inverse tangent of inverse tangent of 0 minus inverse tangent of m. So think about the inverse tangent of 0. So what angle gives me 0 when I take a tangent, and that is 0, minus the inverse tangent of m. So technically we just have negative inverse tangent of m. So let's say we're going to actually look at our limit now. So this means inverse tangent of negative infinity. So think about your tangent graph. Your tangent graph is split at negative pi over 2 to positive pi over 2. So this vertical asymptote is at negative pi over 2, and this vertical asymptote is at positive pi over 2. So we have a negative, bring it down, the inverse tangent of negative infinity. So as we approach negative infinity, the inverse tangent is negative pi over 2. So this equals pi over 2, which is convergent. So that was the first integral. Now we need to go back and do the second integral, which is the integration from 0 to pi of the same problem. So we're going to say note, and we have the integration from 0 to infinity. I think I said pi a minute ago. Sorry about that. 1 plus x squared dx. So we need to write the limit as m approaches infinity. We have the integration from 0 to m, 1 over 1 plus x squared dx. We're going to, again, use that same inverse tangent formula where a equals 1. So we have the limit as m approaches infinity. And we have 1 over a, so that's just 1. Inverse tangent of x over a, so that's just x, from 0 to m. So we have the limit as m approaches infinity. Inverse tangent of m minus inverse tangent of 0. So we have the limit as m approaches infinity of inverse tangent of m minus 0. So what we really have here is the inverse tangent of infinity. So when we go back to this graph, as we approach infinity, we're approaching pi over 2. So this answer is pi over 2, parentheses as well, and it is convergent. So if we go back to the original problem, not the original problem, but our rewrite is the integral from negative infinity to 0 of 1 over 1 plus x squared dx, plus the integration from 0 to infinity of 1 over 1 plus x squared dx. So both parts are convergent. If either part is divergent, we would stop here and write divergent and be done, but it's not. So we're going to take the first part, which is pi over 2, and the second part, which is pi over 2, and add them to be pi, and our answer is convergent. So we're going to stop this here at part A and say that when you have bounds that include infinity, you need a limit. You may need to do L'Hopital's rule, so pay attention to that. Have a great day, and I'll see you in part B.